There are some mics here, right? Somewhere. Bolo. Go ahead.
So and here I have studied about ME design.
Okay.
So basically it is on response performance. So response means stress strain deflection performance tracking. So I want to ask that that a PG grading super pave does comes under ME design or not?
Okay. So good question. The two different areas, PG grading and super, that is based on the material, and mechanistic empirical design, ASTO 1993, Asphalt Institute method, these are all pavement design, right? So the first one is how you select the cement, how you select the concrete, how do you select the brick. Second one is how do you build the house. Do you see the difference? So PG grading is a important component of asphalt material selection for a certain temperature range, certain climatic condition and everything. Now after that, what do you do? How do you design your pavement? That's not PG grading's problem, right? So you are right now what you are studying is the material selection in your MTech courses and stuff. And here we did not go into material selection. We didn't go into viscosity grading. We didn't go. We're just saying, we're just assuming that you select the appropriate type of material. Like I'll give you an example. In America, everything is PG grading, performance grading. But in China, it is still penetration grade. It's something called advanced penetration grade. It is not the basic one, but they have done a lot of research, but it is not PG grading. It is not PG whatever and stuff. So yeah, that's basically two different domains. Yes, exactly. So how do you determine the thickness is, again, my example is how do you design the house, right? How thick of a slab do you need? So you have a load, and then so let's just simplify everything. Let's just make it a beam, a cantilever beam or a simply supported beam. You apply point load, you know the deflection formula, right? So it's that's what forward calculation is we were talking about. So you do the exact same thing. How do you determine the thickness is by saying that I'm going to assume this thickness. I'm going to learn something called multi-layer elastic analysis, which is what this IIT PAVE and everything is. And then you predict stresses and strains, and you say, no, this strain is too much. I need to go lower than that. So I'm going to increase the thickness. No, this strain is way too low. I'm over designing. I need to reduce that and stuff. So it's an optimization process after that. So it's basically application of mechanics to determine thickness. If you go into mechanistic empirical design, in ASTO and stuff, it is all based on empirical, which is something called and number. So a structural number is basically who remembers the formula? Others, come on, PhDs. Sn equal to A1D1. There you go. Okay, plus A3D3M3. So I can't go over all of this right now. So A1 is like a structural, it's called structural coefficient. Okay, so it's basically how good your material. So let's step back. Remember what I said, the old pavement design methods were all about protecting the weakest layer. So in ASTO, you're basically plugging in the resilient modulus of the layer and stuff, and you're saying how much pavement I need on to protect, and that one is for asphalt, it is what, 0.44, something like that, and for base 1.08, something like that, for subbase and stuff. So you are saying every inch of asphalt has this structural coefficient of 0.44. So if it is 2 inches, it is 0.88, right? Let's just say you need a total of whatever, 5 or something. So you have to have a combination of this and this. D is thickness and M is drainage. Let's just simplify it and make it all one. Then you calculate it that way. So that is how the calculation is done. Now your question is very valid. Is this 0.44 valid for all binders I use, for all mixed designs I use, for SMA, stone mastic asphalt, for dense graded asphalt, everything? The answer is no. But that is what you get in empirical design. How do you have a somewhat improved empirical design? Let's just say 0.44 is 1. Let's just say now in the state of Odisha, you have done so much research and so much data collection. You can say, okay, use 0.44 in this kind of a pavement. If I have a really good binder, really good thing, then maybe use 0.46. Maybe if you have a really poor aggregate and everything, maybe make it 0.4. Now what you're doing is you're building on top of other empirical methods with experience. Do you understand? So that is what the pavement design component is. What you are talking about is only about material. So that material constitutes this, right? In mechanistic, what did I say? Delta is equal to function of load, thickness and modulus and Poisson's ratio, I said, right? So your material that you're studying, your PG grading and everything is contributing to this and this. So you determine these and then you do this and this. So well, this is known already, this is the demand. The D is what you determine so that your delta is in a stable range. This is forward calculation right now. Delta is equal to this is that. So if you have an existing pavement and you are measuring delta, then it becomes back calculation to determine E.
So that's why we are going part of that. So this is all under the ambit of grading, or there are other different performance tests on that. All come under that. There are like different levels of mechanical level 1, level 2, so as you said, like this is part of your mechanistic design part. Okay, mechanistic empirical design. One significant part is material connection.
Okay, so good question. A forward calculation is basically when you have all your properties and you are trying to determine response. Okay, a back calculation is you are missing some property but you have some response measurement. So now you are using the response and some other properties to back calculate or to determine the missing component. This is how a traditional equation looks, right? Let's simplify everything. Talk about a simple beam. You have taken structural analysis. I know that, right? No, but you have passed undergrad, right? Yeah. So in undergrad you took that. I'm sure you did. If you didn't, we need to talk. So that's delta, right? That's deflection. Is a function of the length of the beam. There is E and I terms and everything, modulus and moment of inertia, and there is the load. So all of that is your delta. That's the forward. Now let us say in a beam, I am saying that I know load, I know deflection, I know I, which is I is a geometric property. I don't know E. Can you calculate E? You just rearrange the terms, right? That is back calculation. No. ME design is a forward thing. Back calculation is when a pavement exists and you are trying to determine its properties, right? Again, I don't want to confuse you, but back calculation has nothing to do with ME design. It can be anything. Back calculation is taking some kind of a performance, use predict or some of the properties that you should already have. You understand? Let's say, okay, it's a silly example, but let's just say you are a asphalt engineer on an agency. You have all the tests, you have run all the tests, you have all the properties, but then you go on vacation, right? Now somebody else comes and tests the pavement and says, rather than waiting for me for Pushpak to come back so that he can give me the value, I'm going to determine just by measuring the deflections, I'm going to be able to calculate what properties he established. That's back calculation. The only problem is there is no Pushpak in the real world. Nobody has run all the tests. So that data is missing. So that's what you're doing. And the data is not just missing. I mean, it's constructed data. Like sometimes, I don't know how much you all are, some of you I'm sure are familiar with construction practices. You specify 50 millimeters. The actual construction is sometimes 45 millimeters, 52 millimeters. I mean, it all depends, right? So that is going to change your response of the pavement. So that's what back calculation. Good? Better? Okay. We can talk more. I have no problem if you just come and sit down with me during lunch to have questions or something. I love talking, so it's not a big deal. Any other questions, guys? Some couple of you sent me on WhatsApp your more circles, and you were having issues because they were just concentric things and stuff. Did you fix it? Not yet? Okay. Either find me during the break or something, I can talk to you, or somebody like Atanu or somebody, can you just help them? Anybody who solved it, just take a look at it and stuff. I am pretty sure if it was, you're probably not taking the central coordinate and adding it. From my screenshot, I didn't go into details of that. But anything. Any other questions? Sorry about my voice. I got some kind of a allergy attack at about 5 a.m. today. I started coughing and stuff, and I had to take a medicine. We'll see what happens. I think I'm fine, but we'll see. We have a very fun day today. That's what I told you yesterday. We're going to start repeated loading. Okay, and today is all about resilient modulus. We're going to go into the details of the procedure, the mechanics, the test procedure. We're going to analyze different aspects, and then we're going to go into resilient modulus model fitting. What is a model? How do you fit your test data to different models? What are the model parameters telling you? What will you give there? And in the tutorial today, we are going to do two things. One is, I was able to find that back calculation algorithm that is on Python and Google Colab. So the good news is you don't even have to install Python. It's a Google Colab thing. We'll just launch the software and we will together run some cases. I want everybody to run with me so that we will see what's going on, how the back calculation is working. So we're probably going to, if my throat survives, I'm going to probably extend the tutorial a little bit today, because and then I'm going to give you some resilient modulus test results, and we will do an Excel exercise of fitting model, determining model parameters. Okay, and then I can show you how to do it in MATLAB or Python again, and we'll go to that. So lot of fun stuff. Please ask questions. Quick question: resilient modulus testing. How many of you have done? That's a big number. I did not expect that. Okay, that's greater than I have ever had in any class. Okay, so you all are on the hotspot. I'm going to ask you a lot of questions, right? So you're going to answer. especially Tanmay, you are developing a device, you have no excuse. Okay, the Menti link, you may or may not want, I mean, yeah, scan it. I don't have much done today because it's a little bit of a different class, but we'll see. We'll use it most likely. We'll have some inputs and stuff. Okay, repeated loading, resilient response. Do me a favor, can you come here for a second? Hold this table with me. I want to move it there so that I can keep my cup, because oh, the cable. Okay, I just want to keep it here. I put it on the desk and it crashed. Thank you. Yeah. Is it? Sorry. Huh? Out there? Okay. Good, everybody? Okay. All right. So repeated loading. Okay, we are going to talk about repeated loading and repeated loading response and stuff, and we will see what is resilient modulus. I touched on it yesterday a little bit, so we are going to build significantly on that. So there are several ways of you visualizing this. I told you already what is repeated loading, and just for documentation purpose, if it was a cyclic load, then you would have this, right? In a pavement, you are not really applying tension to the material, although you can argue that, when you have the repeated load, the moving wheel load, there is a little bit of, extension happening, but it's not really a cyclic loading. So we don't call it cyclic, we kind of remove all of this, right? Then the question is it just a mod of sine, the loading pattern? If it is just a mod of sine, if the question is, if it was mod of sine, what would happen? This thing would just flip over and then you would have this, right? But that's not how a pavement is loaded either, right? So we use something called a Haber sign. We will get to that. Okay, the loading pattern is known as Haber sign. A lot of people will say, half sign. The answer is no, it is not half sign, it is Haber sign. There is a difference. Okay, we will get into that later. Now let's take a look at what is repeated loading and what is happening. I told you that when a pavement, when a soil element is here and you have a wheel moving, then with time it will have 0, 0, 0, and then you will have some kind of a load pulse, because the traffic, the influence zone, it basically moves from one side to another and stuff like that, right? So that's your load pulse. The question is, you have many of them. So if you look at the time series of the loading pattern on any soil element, then it will basically look like you have this, there is a little bit of a rest period, there is a little bit of a rest period, there is a little bit of a rest period, and stuff like that, right? So there is loading happening and then there is unloading happening. So now let's go to the stress versus strain domain, right? So if you go into stress versus strain domain, this is epsilon, this is sigma. We are trying to load this and then we unload this, and then at beginning there is going to be some kind of plastic deformation, right? So this is written as epsilon P. Epsilon is strain, P is permanent plastic, whatever you want to call it. Then you are going to go load again, come back again, there is going to be some, so maybe this is P1, you now have another epsilon P2. Keep going forever, long time. After some time it's going to become what is known as hysteretic behavior. Whatever goes comes down, comes back. There is no additional energy dissipation happening and stuff like that, right? This amount is called the total permanent deformation that was accumulated on the sample because of all the loading and everything. Then is the recoverable part, or epsilon r, or resilient strain. Okay, resilient strain is here, and then this one, this stress that you are applying is basically the deviator stress. Don't say cyclic stress, repeated stress, but deviator stress, right? So MR, or resilient modulus, is defined as sigma d over epsilon r. Okay, graphically it is the slope of this line. Okay, this is where the basic understanding, and these are questions I usually ask for, MTech final exams, PhD qualifier exams and stuff like that. If I am on a committee, I always ask things like, what is the difference between elastic modulus or Young's modulus? Can talk about it. If you can change it to steel or something. How does it look? It looks something like this, right? You have this, and then you go something like that, think steel. So, but you can still define a E here, right? The question is, what is the difference between E and MR? Let's go. Load is monotonic. Okay, so you are saying if I change this to load, unload, load, unload, load, unload, load, unload here, then that difference will be taken care of. Viscoelastic, I don't know. I mean, it doesn't have to be viscoelastic. It will have some information. So there is the elastoplastic, but if you look at it, even steel is elastoplastic as well. Beyond a certain region, beyond the yield point, it's going to have a plastic behavior. Okay, okay, that's first. Yes, so that's recoverable strain only under repeated loading. But I mean, that's the right answer partly. But if you look at it here, the sample here does not know anything about recoverable or plastic. For here, it is all elastic, right? So, I mean, that's true when you know the whole picture, right? I know I'm nitpicking here, but that's the whole point of understanding it from a mechanics point of view. Where is elastic modulus defined? At what strain level? It's at zero strain, right? It's at the initial thing. There is no deformation induced in the subject or in the material. Here you have already accumulated permanent strain. So it is not at the x is equal to 0 location. It's not. Okay. Now let's go back to the definition of modulus. What kind of a modulus is it? Hint is mathematics, like graph theory. Tangent modulus. It's a tangential modulus. You're drawing a tangent to the stress strain curve. What are you drawing here? It's a secant modulus, right? So it's a secant modulus. It doesn't have it's not just a tangent and stuff, right? And the third one is, yes, it's defined. This is defined under, usually defined under monotonic loading. This is always defined under repeated loading. Okay, so these are differences that you should know. Why it is not why is resilient modulus is not just a Young's modulus, said in a different word, in a term. It's different, right? So we're going to define this. The question is, it's actually a discussion we had a little bit this morning. The question is, what is happening here? What stages are accounting for this in a pavement? Say again? Before traffic is applied, which is what? The compaction, construction and stuff. Ideally, if you have a really well designed and well constructed pavement and stuff, you should have all your permanent strains accumulated, or that's what's called the conditioning of the sample. We'll get into that, the conditioning. Some people call it shakedown and stuff of the sample before you hit the resilient part, right? So repeated loading is going to have two different responses, and there is a way to plot it in another way or another form. What I'm going to do is I'm going to just say number of load application or something on the x-axis, and I'm going to call this as deflection. Okay, what happens is when you first apply the load, deflection increases and then it actually goes down. Actually, rather than this, maybe change this, folks. Let's make it time. It's going to be better. It's going to look better. Let's make it time. It goes up, it comes down. Then after some time, it goes up, comes down. After some time, goes up, comes down. It will happen, it will keep going a little like this. It will not come down all the way. It will go like this, and then there will be a stage when it will become completely recoverable. Now if you take the bottom points of all of these graphs and you draw this, that becomes your delta P, or permanent deformation, right? And everything other on top is the recoverable part. So if you put an LVDT on your specimen, what are you going to measure? Which measure? Deflection. The vertical, which is the total, right? You're going to measure the total. So for every cycle, if you have to calculate a resilient modulus using instrumentation data, it's not as trivial as just taking the deflection and measuring. You have to find out that cycle, was there any permanent deformation accumulation. You understand what I'm saying? So like this, what you have to say is, if it started like this, did it come back to zero, or did it actually do something like this? Because if you just take total deformation, folks, you're going to divide by this whole amount, but you should actually be dividing it by this amount. Does that make sense, what I'm saying? Yes? So that is why resilient modulus devices are very specialized, because they are not just measuring a total displacement, they are actually keeping track for every cycle, the initial value, the final value, and the maximum value. And the resilient is the maximum minus the final, not maximum minus initial, because if you do maximum minus initial, you're taking the total deformation. It's a little bit detailed into test design, but that's what it is. Okay, so you know that every transportation infrastructure is loaded repeatedly, and that is the reason you have to measure your resilient response. So this is a video that I use to teach. This was actually based on some old FHWA video that was made. So for any element, you have as the so as the truck moves, your elements start deforming and then they start bouncing back and stuff. The whole idea is that it should be completely bouncing back when you are operating. Otherwise, you are having what? Rutting, permanent deformation, which manifests itself as rutting, right? You don't want that, right? So this is basically stress versus strain under repeated loading. Again, this is the acknowledgement side. I took a lot from Professor Tumler and stuff, and the whole idea is that it holds for both pavements as well as railroads. This is probably the first time I'm showing this to you all. I don't know, those of you who are not familiar with the cross section of a railroad track, you have the rail, you have the tie, sometimes you call it sleepers in Europe, and in India you call it sleepers. In America, North America, you call it cross ties. Then you have what is known as railroad ballast, which is the coarse grain. So basically below this, folks, you can think of this as base, subbase, compacted subgrade, natural subgrade kind of stuff. Similar stuff. Gradations are different, material is different, load levels are different, thicknesses are different, but the mechanics is exactly the same. There's no difference. So we're going to take a look at this. I talked a little bit about yesterday. You have a confining stress, and then you have a deviator stress coming from the top that actually makes it sigma V. This makes it sigma C, and then if there is no shear, if you are directly on top of the sample, then they can be replaced by your major and minor principal stresses, right? So it's not always the vertical major principal stress, horizontal minor principal stress is true only when the load is directly on top. If the load is moving, the directions have changed, right? So you need to remember that. So that's what triaxial testing typically does that. We talked about this a little bit. There is no shear on the boundaries, and that is the reason we are able to fit principle. Otherwise, it's not true. So be very, very sure about this. Okay. Then there are some other things that we are going to define. One is called bulk stress, or it is also called the first stress invariant. And bulk stress is nothing but sigma 1 plus sigma 2 plus sigma 3, and it is written as a symbol theta. Okay, so it's bulk stress. So bulk stress, if you go into mechanics, it is also called first stress invariant. That's theta, that is equal to sigma 1 plus sigma 2 plus sigma 3. Okay, let's look at a triaxial device, right? What is the relationship between sigma 2 and sigma 3? They're the same, right? So we write it as sigma 1 plus 2 sigma 3, right? What is the relationship between sigma 1 and sigma 3? Sigma 3 plus sigma d plus 2 sigma 3. Theta is sigma d plus 3 sigma 3. Why am I telling you this? Because this will become very, very useful as we go into the model fitting and everything. It's going to become very, very relevant for you, right? So that's called bulk stress. There is another thing we are going to define called octahedral shear stress, but we'll do that later. It's when the time comes. Okay, factor of interest. Repeated loading, I accidentally wiped that, but you saw that in the same plot we were getting this and we were getting the thing, right? So repeated loading gives us information about both resilient modulus and permanent deformation. Only difference is permanent deformation test, which we will cover mostly tomorrow, and among other things. they'll run for a lot longer. Permanent deformation tests are run done under a million cycles, 10 million cycles, 10, at least 10,000. The longest I have run for a paper was 10,000, not longer than that and stuff. And that gives you rutting. Materials, we're going to talk about cohesive soils and cohesionless or like granular materials. They are different. They behave differently under repeated load. Okay? And we're going to talk about testing approach. This is a typical data that you would obtain, deviator stress versus axial strain, for a granular material. And do you see how these shapes are concave up, like how they are like a saucer upward, not the traditional way of plotting? That is because for these materials, as the stress level increases, which is also as the strain level in this case increases, the modulus actually increases. Do you see what I'm talking about? Like if you do a tangential modulus here, you do tangent, 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 the tangent actually keeps rotating up, right? So the modulus value increases, right? So that's called a stress hardening material, right? Because it is a stress hardening is basically you're going to have the tangent rotate upwards. If you had a stress softening material, which is what I drew because that's the most common one when you are explaining the concept, you have the curve going this way. So if you draw a tangent here, 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 it's rotating downwards. Does that make sense? Some of you, it may be completely first time you're exposed to. Please stop me. There is no harm. This is important stuff for a transportation geotechnics class and stuff. So I told you this. We're going to go get into test procedures, but this is a good picture to understand. Remember what I told yesterday about LVDTs and how they measure deformation and stuff? Okay, let me ask you a little trivia. I was talking about shear strength testing yesterday, right? We talked about shear strength testing. If I ran a shear strength test on this sample, what will happen? Experimentalists will know this immediately. Theoretical people will have to think a little bit more. There is a simpler answer. I mean, yes, mechanically, but I'm looking for a simpler answer. Will break. Your LVDT will break because you are on the sample here, right? It's going to bulge. You're going to ruin your LVDT. Your advisor is going to be extremely pissed at you, right? So what I'm trying to say is shear strength testing, you usually don't do on sample deformation measurement because your LVDT is going to break. That is the reason yesterday when you did the data analysis, we were talking about the actuator LVDT. And that is the reason the axial LVDT 1, 2, 3 and radial LVDT data, that was all 0. Do you understand? Because we didn't mount it because it would break. If you do a resilient modulus test, we are now talking about strain levels that are significantly lower than the failure strains and stuff. Now we have all sorts of instruments. Did you raise your hand, Pushpak, or no? So now you are just mounting it around the sample now because you are now interested in the deformation, in the strain levels and stuff, right? So on sample, yes. Can you say that again? No. Haber sign is not. Okay, good point to get to that. Haber sign is this. There is something called Ver sign. A Ver sign is 1 minus cosine theta. Haber sign is divided by 2. And those who are in good at trigonometry and stuff, and if you still remember, what is cosine 1 minus cosine theta? Yes, 2 sine square theta over 2, and now you're dividing dividing it by 2. So it basically sine square theta over 2 is what your Haber-Sign is. Now, if you are asking if this is a Haber-Sign, this is a hand-drawn schematic. I have no idea what it is. It is nothing. It's no, sine square. How will it be negative? Oh, no. So there is a rest period. In always resilient modulus testing, there is a rest period. We'll get to that. What's the rest period? Why it is what it is? We'll get to that. But no, it's not continuous in resilient modulus testing. Okay. So please remember this, folks. And why is this important? Is when you are designing a test setup, saying that, telling the controller, you're doing a lab view coding or something, to tell the controller this is how much load you're applying. You're going to do this mathematics. You're not, if you do like sine mod or something, the magnitudes are going to be wrong, right? So you have to pay attention to these mathematics. Now, is something going to be, in all practical purposes, if you go and work for a company, is this going to be very useful to you? No. But this is what you should know when you are doing a PhD or something. You need to know that what's going on rather than just go on the surface. We talked about this, right? Major load bearing layer for pavements and railroads and stuff. So we need to have one of the design input is layer modulus. Okay, so this is another pitch for things that we have talked a little bit about. How do we do construction quality control in the field? Density. What do we use for design? What is the relationship? Nobody knows, right? So can you do modulus based compaction? Now that's a very open-ended question. There's a lot of discussion in that. There are ways, but it's very complex and stuff. Why does nuclear density gauge even exist? Because it is very fast and it is reasonably accurate as well, and it gives you both moisture and density, right? If you do sand, are you familiar with sand cone tests and stuff? Sand cone test, if you do stuff like that, it will only give you density. You still have to put it in the oven to get your moisture. Nuclear density gauge gives you both of them and stuff, right? So it's a little bit sidetracked. So we talked about this. We have to modulus testing. We can do indirect IDT in asphalt as well to do MR testing. In asphalt, MR is not as common. It is more dynamic modulus that is more common, right? But excuse me, because dynamic modulus is what is known as a complex modulus. It's not just elastic part, but there is. We have already done this, so you know this what I'm talking about. This is the stuff that I tell you about. There are many modulus values that you can determine when you have a stress strain curve. There are many definitions of modulus. There is maximum modulus, there is at certain strain values and stuff like that. But what you are trying to do is you are actually trying to draw in a resilient response, you are trying to draw a secant modulus between for only the recoverable part of the hysteretic loop. So that's the definition of resilient. Okay. Rapidly applied loads similar to those from wheel loads. So let's stop here, and then now we talk about rest period and stuff like that, right? So rapidly applied loads similar to what is done with wheel loads. So how would you do that? Let's pick one of the initial MTech students on that side. I haven't. So you guys are, you said, on the first year and stuff. Okay, so let's I want to ask you, and it's open-ended, so I want you to use your brain, not your previous knowledge. Just think. Okay, I am asking you that tell me what kind of load a soil layer 1 foot below my surface, a soil element is experiencing on this road, on this national highway. How would you determine it? What would you do? And you have all the resources in your hand. I'm not restraining you. You have everything you need, every equipment, every mathematics, everything you need. So how would you determine experimentally what is the stress or what kind of a stress pulse a soil layer 1 foot below is experiencing. Experimentally. Well, we can go back to calculating deformation. I don't think you can do that to calculate pulse, but let's not worry about mathematics. We're talking about experiments. And I said you have all resources. You're not restricted to what you have in your current lab or in your current pocket. You have everything. What do you do? What would you do? You want to phone a friend? Somebody else? Geophysical. Okay. That tells you the speed, yes, and then what? Frequency of the load. It's actually maybe I didn't ask it proper the question, because it should be a relatively simpler answer. Sensor, pressure sensor. So he knows a little bit about probably sensor, so he's like pressure. But the point is, those of you who don't know anything about pressure sensor, you have to have some kind of a sensor that is going to tell me the time versus pressure data, right? Agree? So we are putting on this pavement two pressure sensors, here. Can be pneumatic, it can be piezoelectric, it can be vibrating wire. Well, vibrating wire does not work very under dynamic loading, but yeah, it can be anything. Technology does not matter. It can be servo hydraulic. You can have a air based system where as the system goes, air gets pumped out to something. Anything. Sensors are sensors, right? So what do you do here? You have a thing moving like this with time, right, folks over there? Time, you have, it's at the top, so it's coming, and then it has some kind of a pulse, goes down. The bottom one, probably coming, some kind of a pulse, goes down. Why is it wider? Because the stress dissipation works like this. So this one, even when it is here, this element is feeling the stress, whereas this element is not feeling the stress. On the other side, it's exactly the same, symmetric and stuff, right? So that's the reason as you go down, the stress pulses become wider and shorter, less magnitude. As you go to the top, narrower and taller. Now the question is, you have a layer like this, HMA, base, subgrade. Somebody who knows resilient modulus testing, you have run it, right? What is the rest period you use? What is the pulse and rest period? Do you remember? 0.1, 0.9, right? 0.1 second. We'll get to that. People who don't know, we'll get to that. Don't worry. 0.1, 0.9. Is that for base? Is that for subgrade? Is that for everything? Is it 2 inches below, 5 inches below, 6 inches below? Where is it? Asphalt layer? No, you don't run resilient modulus test on asphalt. I'm talking about ASTO T307, which is what we're going to go, like the actual testing that we did with the lab. For granular, have you done subgrade testing? How many of you have done aggregate versus subgrade? What? You have done aggregate, I know that. How many of you have done subgrade soils? What do you do? So one of you is wrong, right? The code says the same, so that's our excuse, isn't it? So the point is, it's if you actually go and track the rest period and the pulse width, it should change depending on where you are in the layer. If you look at the code, the subgrade, yes, it is acceptable to do it at 0.1, but it's actually also recommended to do at 0.2 and 0.8 in Astro T307. Whereas aggregates are usually 0.1 and 0.9. That's the reason, because they are above the subgrade and the pulses are going to be a little narrower. And the stress states are different for sure. That we all know, we all agree and stuff. So the width is going to be different. That's one thing. But again, we have to pick something. So they had to pick something. What does the width depend on? Pushpak, what does that width depend on? Like this thing, I said I put a sensor. One thing you already know is the depth. We know that. What is the another thing I did not tell you? The width depends on. No, the width, not magnitude. I'm not talking about this. I'm only talking about the time domain, time axis. What does it depend on? Speed. Speed of the vehicle, right? If the speed is very high, it is going to be very short. If it's much higher, it's going to be much lower, then it's going to be much wider, right? So now you're talking about 0.1 second versus 0.9 second. What speed does it correspond to? What speed is it? 80, 45 to 50 miles per hour and stuff. Do you always drive on 80? So should you always drive on 80? So you have to again set codes for certain values, right? So it was just done by research and stuff, and they develop it for 45 to 50 miles per hour, which is 80 mph essentially, right? Why the rest periods? Yeah, there is a gap. There is a gap between the load, vehicles and stuff, right? So rapidly applied loads. What is rapidly applied? 0.1 second is the load pulse, 0.9 second rest, then 0.1 second, 0.9 second. So in another very important question, because these are things that, you know, this course is also supposed to open or give you directions for, you know, looking into problems, future research, or exploring and stuff. Do you know what frequency of loading is? You know that, right? Right? A sine omega t and stuff, you know what the frequency is and everything, right? Omega is what? 2 pi f, right? F is frequency, right? So what is the frequency of loading when I have a sinusoidal wave of this and this? Hold on, don't say anything yet. When the time period is, this time period is 1 second. What is the frequency of loading? 1 hertz. 1 cycle per second. Everybody agrees. Now I am doing this 0.1, 0.9. What's the frequency of loading? Is it 1 or is it 10? How much are you loading actually? Are you loading it in 1 hertz, 1 second, or 0.1 second? 0.1 second. So it should be 10 hertz, right? Yes, but I mean, when you're loading the sample, does it really know that a rest period is coming? It doesn't, right? So is it 1 hertz or is it 10 hertz? Nobody knows. There is actually no agreement on that, right? People have talked about it different ways. So frequency of loading, when you have a repeated loading, is not a trivial matter. It's not a circle that you can just define, cyclic loading and stuff like that. It's not, right? And how does it affect speed versus that? Because, oh, by the way, one more thing I did not say, I think I should say, because we are now getting into the details. We talked about this width depending on speed and depending on depth. What is the other one I mentioned left out? Say again. Upper layer stiffness, not the same layer stiffness, the upper layer stiffness. Why? Because that determines at what angle is this load is going to get dissipated, right? Sometimes people say it's 45 degrees or something like that. That also can change, right? So your modulus or the load pulse can change between a summer and winter when your asphalt layer changes stiffness or modulus by a factor of 10, like 400,000 psi to 4 million psi. It can happen, or 2 million psi. So your pulse width is also going to change, right? So rapidly applied loads similar to those from wheel loads. So you're trying to do your best job to simulate that. Relates to elastic component of response only. We talked about that. We're taking care of the plastic. We're eliminating the permanent. What is the difference? We talked about this already. Lab test, ASTO T307, which came out of Sharp P46. It can be done under undisturbed, disturbed, or something. So when you are in geotechnical, like pure geotech, undisturbed sampling is a very, very big deal, right? In pavements, it's not. Why? Yes. Harder does not mean we should not do it, right? Harder. Difficult to get an undisturbed sample, but if the geotechs can, we can too, right? But the point is, the answer I was looking for is when you are doing a pavement construction, you are anyway compacting, you're anyway mixing it, you're anyway scrapping it stuff. So it is always reconstituted, remolded, and stuff like that. So there is no, it's not really undisturbed in resilient modulus test. So there are different protocols. There is ASTO T307. There is something called harmonized protocol. We'll go into that a little bit, and then we are going to. You can also do correlations, and mostly, I can guarantee that when you go to practice, even in India, it's mostly about correlations and other relationships, right? I'm pretty sure the agencies don't run it very regularly. Nowhere they do. Even in America, most of the agencies don't run it regularly. Okay, so it's a fundamental problem. Well, here, I mean, this is just some survey results. How do you determine what kind of laboratory specimens? There are some people who actually did undisturbed from rehabilitation designs, laboratory fabricated mostly and stuff. The fundamental property, it's a rational test. It considers the effect of density, grading, fines, shape, water content, all of that. So you can actually represent your actual soil or your aggregate, and then you test based on that, right? And end result is you should provide a value to your pavement design or your pavement rehabilitation, saying this is what you have, and then you go from there, right? So then let's talk about the test procedures. The primary one we are going to focus on is what is known as ASTO T307, right? So T307 is it has two types of materials it considers. They are called subgrade solid unbound granular materials, and or type 1 and type 2 and stuff, and we'll look at that. And the test procedure or the test method is slightly different between the two, and we'll, in terms of magnitudes and stuff, and we'll go into that. First of all, conditioning. You have a reconstituted sample that you compacted in the lab, right? And then you're going to test it. So that's basically before you get into resilient response, you have to have your initial compaction done, right? What is that simulated through? That is simulated through your lab compaction, and anything remaining you should be doing what is known as a conditioning stage. Compaction vehicles, are they heavier than regular trucks or lighter than regular trucks? Heavier usually, and they are running directly on top of the layer, whereas trucks are running on the asphalt layer or on the concrete layer, which is dissipating the stress. Is conditioning, you should be applying definitely greater magnitudes of stresses, because compaction and initial reorientation happens under greater stress levels, right? So that is the reason you have sigma 3 values. We'll talk about it at 15 psi or 103 kPa. Sometimes, depending on other methods, it can go up to 300 kPa. Load pulse 0.1 second duration. People talk about 0.5 to 20 hertz. Again, that depends on the relative difference between rest period and loading period and stuff. And then the loading can be using two different methods. One is called constant confining pressure, which is the most common thing you see, and then the other one is called variable confining pressure, and we'll get to that a little bit. Okay. Well, we'll get to that right now. This is what you see, Astro T307. Yes. Frequency should be lower. Ideally, yes. Ideally, if you're trying to do that, but the method just uses the same frequencies. But you are right. The compaction speed is very low and stuff. So you should have probably load pulse depth width should be wider. So this is for Astro T307, and this is how this plot is. So this is horizontal stress or confining pressure in this case, and then you apply, this is in psi folks, so just bear with me. This is basically 21 kPa. You can multiply by 7 on an approximate. It's 6.9 but close to 7. So 3 psi you apply, and then your deviator stress is 369. Okay, at the same value, at the same confining pressure, you load it by 3. Okay, so let's go over the procedure first, because otherwise this is going to be difficult for you to understand. So in the procedure, you have stage 0. This is going to be stage number 0, and we are going to call it conditioning. Okay, usually it will have some kind of a sigma 3, some kind of a sigma d. We'll look into that, and then we're going to take n is number of cycles. Okay, so something we'll look into that. But conditioning is usually 500 to 10,000 cycles. What I have done most commonly in my life is 1,000 cycles conditioning. There is requirement that after conditioning you should not have permanent deformation more than this and stuff like that, but with a well compacted sample, 1,000 cycles usually work. Then you go to sequence number 1. Folks, these who are being exposed for the first time, this is going to be important, because this is very important to understand resilient modulus. Stress sequence 1, and I'm talking about the very first one, and just write down units please, because I am much more familiar with these numbers. I can go quickly on this. It's 3 psi, 3 psi, and you apply 100 cycles, and every cycle is, how long does it take? 1 second. So the test, this sequence takes 100 seconds, which is what? 1.5 minutes, 1 minute 50 seconds, right? Then you go to 2. Keep 3 psi, deviator goes to 6, again 100 cycles. Keep then 3, keep 3 psi, deviator goes to 9, again 100 cycles. Okay. After conditioning, how many sequences did we just talk about? 3. There are 15 such sequences. Okay, we'll look at the values, and in the tutorial today also we'll look into that and stuff. So after conditioning, don't worry about conditioning, the test has right now 3 sequences right now, and during the sequences, what did we do with the confining? Kept it constant, hence the test is called CCP, constant confining pressure. Okay, and then the next step is going to be 5, 500, and we'll go to that, no need to write this down, but again we'll have 4, 5, 6, it's going to be 5, 5, 5, so again another 3 with the same constant pressure, that's 35 kPa basically, 21 to 30. I know you're calculating if 5 is correct or not, but yes, it is correct, that's what 5 is. So 5 is constant confining pressure, again number 3. So do you now understand the top graph, what is going on? 3, there are 3 data points, 5, there are 3 data points, 10, 3 data points, 15, 10 data points, 20, 10 data points. 5 times 3 is, so that's 15 cycles of constant confining pressure. So the slope is vertical, I mean infinity, basically the lines are vertical. There is another method called NCHRP 1-28A, which actually says that, hey, that's actually not a very right characterization of your material. In your material, you should not keep constant confining, you should change confining as well when your vertical stress is also increasing. So in this case, your slopes don't stay same, it's 3, 6, 9, 3, 5, I don't know why, or is it 6? I don't remember the numbers, don't get me on that. And then 10, 15, 20, it actually, as the y-axis increases, the x-axis is also increasing. Okay, so you can do this. This actually is meant or is supposed to be a better representation of actual testing or actual what happens in the field and stuff, but it was not really widely adopted or anything, but we still have a document called for this. Okay, that's the concept of VCP, variable confining pressure, because the lines are not vertical anymore, it's changing from state to state, it's changing. Now the question is, I still haven't defined to you how do you calculate resilient modulus for people who are new to this method, right? How do you do? For every cycle, what do you have? You have basically this. Why am I doing this? I have already, well, maybe I should not do this. I should have the axis here. So you have already moved past, you are somewhere here. Now you are in a hysteretic loop. For every cycle, you have sigma d and you have epsilon r. So for all 100 cycles, you can calculate mr, which is sigma d over epsilon r. But the test procedure says that out of the 100, you take the last 5. 96, 97, 98, 99, 100. That 5 you take the average, that is what your resilient modulus reported is. For every cycle or for every stress sequence, you take cycles 96 through 100, take the average value of, did I write it somewhere? Average of sigma d of epsilon r for each of those cycles, and that you report as your resilient modulus for that sequence. How many sequences are there? So how many resilient modulus values are there? So if I ask you what is the resilient modulus of this material, what do you say? It depends. Tell me the stress state. What stress state is it? Right? E is equal to 30 ksi or 30,000 psi. That's a elastic representation. That is not resilient modulus. Right? Resilient modulus is not one value. A material cannot have a single resilient modulus. You can take a representative modulus. That's a different thing. We can talk about that tomorrow. Today we'll not have time. I will probably talk about that tomorrow actually. And you will see is representative modulus is different because you are trying to take one value to represent. It's like this, right? What is the average, like what is the height of a student in this class? It changes, right? So you have to take an average or you have to take a 50th percentile, whatever you want to do, right? You are doing something representative. But that's what resilient modulus is. This is what VCP is. This is what CCP is. And test setups, traditionally, when systems were developed, and I think that's true for even the system that you still have the out external LVDT, right? Yeah. The simplified one I have is also external LVDT. Your LVDTs are outside on the system. It's not mounted directly on the specimen like this. Okay, but in Astro T7 allows that. Astro T307 allows external LVDTs. But if you go to NCHRP 1-28A, the harmonized, it says do not have LVDTs outside. You have to have LVDTs on the specimen. That's because there can be rotation of the specimen, there can be compliance of the loading load and stuff like that and stuff, right? So this is how. And if you do axial LVDT measurements, you should have it at 120 degrees across the specimen, three LVDTs, so that you measure rotation or tilting and stuff like that. Just a representation. Again, 60 repetitions per minute. There is a reason I don't say 60 hertz or whatever. I mean, I don't say 1 hertz or something because that's not really what very well defined. There is another thing that I did not tell you. When you load a specimen, I said your confining pressure. Let's just go to the very first stage. Okay. Sigma 3 is equal to 3 psi. Sigma d is equal to 3 psi. Okay. What did I say about? Okay. Oh, by the way, is this a stress controlled test or a strain controlled test? Stress controlled, right? Because you are not specifying how much strain to apply or how much deformation to apply. You are telling how much stress to apply. So strain to measure, exactly. Strain you are measuring. It's not control. Talking about what are you controlling it, right? So it's basically you're telling your car to go at 60 miles per hour, and then you are measuring your fuel economy, something like that, right? What are you measuring versus what are you controlling? Now my question is, yesterday if you paid attention, I alluded to this. I said a device only knows how much to move because displacement is an absolute measurement. This is 0, this is 1, this is 2. It's very easy. Force is not an absolute measurement. Force is dependent on my material. If I'm trying to push and my hand is moving, force is 0. Whereas if this is constant, it's very big, right? So the question is, even if it is a stress control test, in the background the machine is actually going by movement. There is a problem with that. 0.1 second is this, very quick, right? And now I am trying to target 3 psi, 5 psi, you will see the maximum value is 40 psi, right? You have to do very quickly this, and when you do that and the sample comes or the rod comes and it hits it, the sample is not just deforming by the applied load, it is actually deforming or getting damaged by the impact, right? Which is not good. You don't want that. Your truck is not jumping on the road. The truck is applying a seating load and it's pushing against the load, right? So the question is, how do you ensure that? You always apply what is known as a seating load. So for every deviator stress, it's usually 1/10 of it is seating and 2.7 is the actually mechanically applied pulse load. Why? What happens if the seating is 0? Raki, what happens when the seating is 0? Think about the specimen and the rod. What happens when the seating is 0? No. How much? What? This is my rod. This is my specimen. Seating is 0. So is it touching? No. So you're losing contact. And then you're coming and banging it. So the moment you have seating is 0, you're going to lose contact in your feedback system. You never do that. That is the reason your code or your testing method always has a seating in there. Seating in there, right? So that's what this is. Seating load is 0.1 of the deviator, target deviator. So that's something that you really need to do. Okay, I've already told you this. Again, experimental people who are getting into design, testing and stuff like that, when you don't meet the shape, when you play with what is known as PID settings of your test systems, it actually tells. Because what is a feedback system, folks? Think about it this way. It's very simple. A feedback system is, it's like your you guys are all young. Has anybody ever had an antenna on your TV? Do you even remember what an antenna of a TV is? Right? Have you ever had to go up the roof and rotate the antenna to catch signal? So a feedback system is that. Aaya kya karke, you're just rotating, right? Ha aa gaya, ruk jao, basically. That's essentially what it is, a feedback system, right? You're just trying to go back and forth, back and forth, back and forth, right? So the point is, if your feedback system is not giving you a good load pulse, then you have to adjust what is known as proportional, integrative and derivative gain of the system, or PID system. That's equipment design. We are not going to go into that. Told you this already. Second modulus, load distribution, sample preparations. Specimens are, dimension is dependent on particle size. Those who have tested subgrade soils, you're probably talking about 2.8 inch diameter or 4 inch diameter, which is 100 mm or something like that, diameter. And then the height is usually double of that, 100 by 200 or something. Aggregates, they get bigger. To have a proper representative, you should have at least 4 to 5 times the Dmax and stuff. So for aggregate testing, the minimum you can do is 4 inch if you have a fine grained aggregate. The moment you have a bigger grain, you are going to 6 inch diameter. 6 inch diameter by 12 inch tall, which is pretty tough to work with usually and stuff. But that's what specimen preparation is. Okay, this is our stress sequence for type 1 or unbound aggregate materials. So I told you this, so you should now be able to read this with me. So 3 psi, 3, 6, 9, 5 psi, 5, 10, 15, 10 psi, 10, 15, 20, 15 psi, 10, 15, 20, 20 psi, 15, 20, 40. What did I just say? I just said the psi numbers. You just divide by 6.89, you will get those numbers. That's what I'm saying. Okay? That is what a full unbound aggregate test setup sequence ASTRO T307 looks like. Make sense? Should we test subgrade soils under similar stress values? Where is the subgrade in the pavement system? Yeah. Question? So go ahead. Can we do for bound materials? Yes, you can do, but these stress states are defined for unbound aggregates and soils. Bound materials, it's a good question and it can actually be very long discussion. What do you mean by bound materials? Because if it is bound material, if it is 100% bound, technically it is not stress dependent anymore. Stabilized material, yes. Stabilized materials, yes. I haven't tested. Have you tested it? Do you apply similar stuff? Yeah, but you're probably talking about very less percentage of cement, right? I mean, talking about 2-3% cement or something. I have never run those tests, honestly. So, okay. And do you apply confining, like similar stuff? Okay, okay. So people do it, but ideally it should also stand without confining. I don't know if confining pressure has an effect or not. I mean, my knowledge is going to be literature based. I don't have personal experience running stabilized. Very less. It's probably non-existent because it is standing by itself. But does the modulus depend on stress state on that? Whatever you tested, is it still a stress dependent material? It is, okay. Yeah, I haven't tested stabilized ever. So I hope that answers your question. So they're applying similar load levels, but we don't have like special specifications, at least to my knowledge. Oh, so this is the University of Illinois. Okay, this is another interesting point that I did not say. Okay, before we talked about this table, I forgot talking about this. This is the conditioning. The conditioning is done at sigma 3 is 15 psi and sigma d is also 15 psi. So what is sigma 1? 30, right? So let's define a very crude term. It's called torture index. Okay, how much are you torturing the sample? And torture index is defined by sigma 1 over sigma 3. How much confining you are applying versus how much large vertical stresses you are applying and stuff like that, right? So in this case, in the traditional conditioning, it is 2, right? 30 divided by 15. Yes? If you are trying to shake down a material, if you're trying to get rid of all the permanent deformation and all completely rearrange the particle and stuff, research has shown that if you do increase this value, it will actually shake down the material really well, it will actually pack it really well, and it will actually become a lot stronger, as long as it's not failing and stuff. I mean, you can't apply a ratio of 8 and stuff. That's going to probably fail. So what they did is, this is actually another of Professor Thompson's work. He actually did Sigma 3 is 103, but sigma d is 310. So 310 divided by 8 is what? 35? No. What's that? By 7, sorry. 45, right? 310 divided by 6, 7, it's basically 45. 45 psi. So what he did is 15 psi of confining, but he applied a deviator of 45 psi. So it's holding the material really well, but it is just pushing it really hard to pack it really well and then get a well compacted, well conditioned resilient modulus response under this torture index of 4.0. So basically, remember yesterday how we calculated subgrade soils and stuff? They are not very well confined because it's only about half a psi of confining pressure we calculated yesterday and stuff. The whole idea is during compaction, the more you push it, the more you condition it, the more of a resilient behavior you will get. So that is how this was defined. Again, this is a research test method. It is not a specification. So you can't write an AASHTO and stuff. It was just a research method, and it was developed. So again, this is the same setup I showed you yesterday. These are the LVDTs. This is the shear. This is after shear strength testing. Usually, by the way, you probably, if you look at the test specification or even your vendor equipment manual correctly and stuff, usually resilient modulus is a non-destructive test, right? It is much very small strain levels. So you can actually, after resilient modulus, you can actually run a shear strength test on that same sample, as long as you don't have LVDTs mounted and stuff. If you don't have it, you can run the same shear strength and you get 2 data points for one specimen. So this is after running the shear strength test. It's 11:12. You want to take a break now? I think we can take a break because now we are getting into test results. I think the procedural part is over. We'll get into test results and then we'll get into models and stuff. Let's take a 15-minute break and come back. Thanks. Okay, let's get started. 1.5 more hours to go, and I think we'll be okay. So let's take any questions on whatever we had. I talked to a couple of you already, but any other questions? Yes. Ideally, it is okay. Good question. Will the resilient modulus change between the two test procedures? Probably yes, right? Because now it is much shaken. But what is more representative of what is happening in the real field? Their argument is that the higher torture one is actually more representative because you are actually shaking it under bigger stresses. So that's the reason I said it's not a specification test, right? It's a research test. So maybe the numbers are different. I don't have the comparison. So let's take a look at some data, and then we're going to see some factors, and then we'll get into models. We should be okay in terms of time, because I want to get to know models for sure. So this is 4 different materials. CS6 is a typical dense graded aggregate base material. Ca11 is more of a sub base material. There is P gravel stuff, and you do optimum water content. The T80, T180 is your modified compactive effort in terms of kilonewton per meter cube and achieved water. This is something, again, experimenters, you need to really understand your optimum water content and the dry density. This is the density established. When you're doing modulus test, don't just report this, always report the achieved values, because that is what the sample actually knows, right? There's also a very big difference, those who are working with aggregates especially, very big difference between added water and actual water retained in the sample, right? Never ever report just added water, because water drains. So when you are testing, after that, collect sample. I used to just take the entire sample and put it in the oven, much easier. So that way there is no question of did you take a representative sample. I just put it in a big tray, throw it in a big oven, get it next day. It's my actual tested water content, right? Don't just report this because it's not correct. Okay, this is how you plot resilient modulus. Many different ways. This is plotted on deviator stress. So think about it this way. What did we say? 5 different confining pressures and 3 deviator stress per confining pressure. So for a resilient modulus test, you will have, for a given material, you will have 5 different lines for deviator stress, right? And it should ideally, and we're going to talk about that bulk stress and stuff, it should ideally increase as the stress values increase for a coarse grained granular material, stress hardening material. Crushed stone, it goes all the way up to say 350 in this case. So 350 megapascal is about what, 50 ksi, 50,000 psi and stuff, which is on the high side, I think. My maximum values probably have been something around that range and stuff. Okay, type 2 subgrade materials, right? Now we are talking about finer grained materials, and they're subgrade mostly. Now the question is, somebody can say, hey, if my base is actually like up in the pavement, also I have a fine grained material, of course, test it using whatever the stress states are applicable and stuff. 2 inch, 2.5 inch, 4 inch, typical. Can you run a 6 inch sample? Of course, yes, but you know, who have run big samples, it's very difficult. So you always try to avoid size effect while at the same time making it representative. Compaction is different. How do you compact? Aggregate testing people, how are you compacting your samples? Vibratory, like a jackhammer kind of thing? Is that what you're doing? Okay. Standard. It's very difficult, by the way, sometimes to let's have a little discussion. How do you target density for your samples? How do you do that? Speak up. How do you make your sample? How do you specify target density and how do you meet it? Okay. So you don't. So how do you compact? Is it a constant duration, like maybe 5 seconds, something like that? Uh-huh. So you report the achieved density, or do you report the target? Okay. So there are different ways, like, for example, the way I used to run it is I would calculate the target density. I know the volume of the material, and then I would say I'm going to compact in 5 layers. So I know the mass for every layer, and I know a target height of the every layer. I do not stop compacting until I meet that. Now the question is that, do you have a soft aggregate? If you have like a limestone and stuff, your aggregate may crush. That's one. Excessive compaction may crush your aggregates. That's one problem, right? Mine, where that was not a problem. I always had, so I just meet it. So it's difficult. That's what I'm saying. Your achieved density is never going to be exactly the same as your standard and modified compaction and stuff. And there is a big difference also, folks. How do you do what a Proctor test or standard compactive effort and stuff? You have a little hammer, right? What's the footprint of the hammer? It's only part of the mold, right? And then you drop it here, and if it is open graded or something, it bulges here. You drop it here, it bulges here. You try to play with it, right? So Proctor or that test is not very representative usually of an aggregate specimen. Very difficult. And when you are compacting your resilient modulus sample, what are you doing? You're putting like a plate or something, right? And you're doing a vibratory compactor on top of that. So in this case, you are applying compaction to the entire surface, whereas in the Proctor test, you are putting only part of it. Do you see the difference in that? So the energy implied is also very different. So number of blows may not always translate the same way. So be very cognizant of these things. These are challenges. You have to have target densities and stuff. Subgrade, it's sometimes relatively easy. I have done it using the same kind of approach. You can do almost like a Marshall press or something. You can take it and then just press it. It's much easier for subgrade because you can compact, carry it to another place and set it up. It's easy aggregate. You have to have vacuum, otherwise it's going to fall apart and stuff. It's just a lot more challenging. But and either way, membranes also have a very significant effect. Aggregates, the membranes get punctured sometimes, so you have to have 2 membranes. Subgrade soils, it's much easier and stuff. So this is how it looks. Stress states 500 to 1000. Here also sigma 3s. Sorry, this looks at S because Macintosh sometimes does not read sigmas very well. This is S stands for sigma. So sigma 3, sigma D for conditioning, as you can see, it's significantly different. Look at the stress states and tell me the primary difference you see. Yes, they are different in value, but tell me 2 primary differences you see. Say that again. Yes, 5 3, like number of stages confining wise, it was 5. Now it's 3, right? That's the first one. Second one is, no, value is less is yes, but there is, yes, it's a decreasing pattern. You are now testing it is a decreasing pattern. There you started at 3, 5, 10, 15, 20. Now you are doing 6, 4, 2. You are decreasing. Okay. Again, 15 stress states, very similar. So that was a 5 into 3. This is 3 into 5. 3 confining stresses and 5. And again, sequence numbers exactly the same, 1, 2, 3, 4, 5 and stuff. Nothing difference. You can actually have unconfined as well. As I said, you know, I have showed you that at the subgrade level, the subgrades are such small confinement. So to represent that, to model the worst possible thing, again there is a method where they don't actually apply any confinement in the conditioning. They just unconfined, they just bang it. So it's just again torture. Remember sigma 1 over sigma 3. That's basically what I call. So this is the device that, you know, we used back in the day. My device is different. Where is MR testing now? It's a very old research method. People have been doing it very long. You know, I am very pleasantly surprised to see so many different people have done it. How many different institutes, by the way, here? So raise one per person per institute. So IIT Bhubaneswar, just one person raised hand. Just one. Okay. Okay, let's do that. IIT Bhubaneswar. Then there is SVNIT, right? Surat. So you guys have set up as well. 2. Then there is IIT Chennai. 3. What's that? Raipur. 4. You also have a setup for that. So 4. And Burla also, Varanasi. You also have 1. 5. You have 1. 6. Man, that's okay. So, but I mean, yes, most universities also have, but I don't see that many students. I guess it's a transportation geotechnics class. Yeah, I understand. But I'm very pleasantly surprised that you all have played with this. It's a very expensive piece of equipment. It's not very easy to buy at an agency level all the time. It takes a lot of time. It takes a lot of training. You have to basically babysit the thing. Like, you know, I'll show you my device tomorrow, the one that I used to use, and the specimen you have to put powder around it so that there is no friction between the two membranes and stuff like that. And my advisor used to joke is that, hey, you're far away from getting married or anything, but look, you're already taking care of babies and stuff by putting powder and stuff. So it's literally babysitting and stuff. But it's good. It's a good device. Fine grained soils. It is stress softening. So this is how, again, master students, initial PhD students, this is the kind of thing that you may be asked depending on what you are being asked. Linear elastic versus stress hardening versus stress softening. How the modulus changes, how the shape changes and stuff. Pay attention to those. How is modulus modeled? And you can do this in several different ways. So this is for fine grained soils, and there is a thing called ERI, which is something called breakpoint modulus. We'll get into that. But as the deviator stress increases, you plot it against deviator stress for fine grained soils, you'll see a decreasing trend. It's a stress softening material. There was a called the hyperbolic model. It was also used for resilient modulus versus deviator stress. Again, it depends on people. So let's step back a little bit. What is the purpose of all of these models? What are you trying to do? Why are you characterizing the material to determine resilient modulus? Is because you want to do an analysis. You want to do some kind of computation, right? And in that computation, you are going to have stress that is going to change from one point to another and stuff like that. And let's revisit that, or let's take a look at that and see what it means. In your traditional pavement design, right? Let us say this is your HMA and this is your load, right? And then the stress is being dissipated like this. Yes, the slope will change at the interface, but I'm ignoring that in this case. So you know that between this point and this point and this point and this point, the stress is different, right? When the stress is different, that actually means that your modulus is also different. It is a stress dependent material. On the other hand, if you are doing like an ASTO design or any other design, in fact even in the MEPDG for now, you are saying that E is equal to 30,000 psi or something like that. What does this mean? Where is it? Right? In an aggregate layer, if you just model an aggregate like a very thin asphalt surface and then just aggregate and you do an axisymmetric model, you will see that in this area, this is axisymmetric, so there is a pavement on this side as well. I'm just drawing the boundary at the end at one side. So if you see, the stress actually keeps decreasing over here. So if you plot the resilient modulus heat map or resilient modulus contours and stuff, you will see that this is very high numbers versus as you go down it is very low numbers, right? So if you do that, now you are calculating your response and stuff like that. If you assume just one modulus value, and at certain points you are under predicting or underestimating the modulus, at certain points you're way overestimating the modulus, right? So you have to reflect that. So that is the reason people have a way, or people develop models to capture how I can calculate modulus knowing stress states, right? So what you can do is MR, we're going to look into that, but there is a model called K theta model. So it's basically K theta is to power. We'll get to that. Don't worry about the model for. What you're trying to say is, what is theta? We already said that, right? Sigma 1 plus sigma 2 plus sigma 3. Why do you get sigma 1, sigma 2, sigma 3 from? That's your forward calculation, your analysis, your layered elastic analysis. That's like not simple, but that's trivial stuff. You know that already. So at any point you are going to be able to calculate sigma 1, sigma 2, sigma 3, and then you are going to be able to calculate theta, and then you are going to put into K theta raised to power n, and then you're able to determine modulus. But I have a question. I know what you're asking. I'm going to ask that question, so you can't ask me. How do you get sigma 1, sigma 2, sigma 3 in the very first place? To run your forward analysis, what do you need? Modulus. I thought you were determining the modulus. That's what you're asking, right? So what are you going to do now? Seed modulus, right? So let's talk about that a little bit. So this is, it's a little bit deviating, but I'm glad that you all, most of you are at least following up. So let's go there. I like this discussion. So I am going to assume E is equal to 30,000 psi. Okay? I'm going to run the forward calculation, like layered elastic, LET, layered elastic theory is what it is, LET. I run it. So at every point I'm going to get theta now, sigma 1, sigma 2, sigma 3, right? Now I can get, from that I will get MR distribution at all the points, right? And then that MR I'm going to calculate, let's just say that MR at a certain point, maybe at the midpoint, let's just say my target is the midpoint, that MR comes out to be 35,000. Let's say it comes out to be 35,000. I started at 30. So I rerun this with a value of 32,500, which is the midpoint of the two. Then I again calculate theta. Then I again calculate resilient modulus. then there is a difference. I take again average, I again run it until I converge. Then I know this is my right representative modulus value. Right? This is what you are doing in LET, layered elastic theory, because you are assigning only one modulus per layer. Life becomes very easy if you are running something called a finite element model, because now your values can change every node, right? And we'll get to that. We'll do on day 5, we will do IIT. You'll see what it does, and you can actually plot. Are you following what I'm trying to say? Modulus is not that easy of a thing to chase down in unbound materials, right? It's a little bit tricky. You have to iterate. Okay, most most subgrade soils, if you plot the resilient modulus against deviator stress, okay, you see a kind of bilinear behavior. Okay, now some people call it bilinear, some people call it piecewise linear. I'll leave it to the mathematicians to decide what it is. I have always called it bilinear, but recently I have been taught on completely different topic that it should be piecewise linear. Not for this, but basically until a certain point, which is called break point, the deviator stress, and from experience it is close to about 6 psi, just empirical. There is no physics behind it. It's about 6 psi. Okay, you have a very rapidly reducing modulus. Beyond that, it goes a little flatter. Okay, so there are bilinear models. We'll take a look at models. So this is how the model looks: K1 plus K3, K2 minus sigma D when sigma 3 is less than K2, K1 minus K4 sigma D minus K2 when sigma D is greater than K2. It's basically just, this is just defining the two equations. No rocket science in it. And when we play with IIT, we will look at this in detail and you will know exactly what's going on and what not. Okay. By the way, you have seen some places the ERI, and I said I will tell you later. The ERI basically is this break point modulus, this K1 value. At what point is the modulus breaking? It's just in subgrade soils they use. Okay, so this is again couple of North Carolina airport, some tests and stuff. You can actually fit bilinear models. How do you fit the bilinear models? You just do it like eyeballs and stuff. You just see these are in linear. You just see these are linear. There's no defined break and stuff. Other MR models for cohesive soils, again we're going to skip through this very quick because we're not going to use this. I want to get to the models that we are going to use so that we can spend some time on it. This is Brown's model. PQ, anybody advanced geotech classes, stress paths and stuff like that, right? You have taken classes. We're not going to get into that. Stress paths, and stuff. That's PQ models and stuff. This is Dawson Gomez Correa model. Again, when I give you the slides, you will have it for reference, but I have never used this in practice myself. Empirical correlations, you have seen this: 1500 CBR, 17.6 CBR, 0.64, 1155, 555 R, ERI is with QU and everything. This is again, folks, let's see your memory. What level of MEPDG is this going to be? Mechanistic empirical, I said there are 3 levels of designs, remember? What? This is 2. This is 2, right? You test something and you are predicting something. That's what this is happening, right? But again, I think by now you all know we should not be using CBR to predict MR because it's a different test, blah, 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 all of that. But when you don't have anything, you have to. Just have to, right? What are the primary factors that affect behavior? Sigma D, sigma 3, moisture content, plasticity index, clay content, high density, freeze thaw effects, they affect your behavior quite a bit and stuff. Some results, I'm going to skip through this because we're going to get into models now. Moisture effects, again, if you see wet of dry of optimum, it's very high. As water increases, its status collapse stuff. So it's just standard observation and stuff. Let's go unbound granular materials. I told you this is stress hardening. This is what I was trying to get into when I told you, and we're going to see this on Friday. We're going to do this on IIPAVE. You will do it on your computers, and you will see this. Look at how the modulus at the so this is an axisymmetric, so load is right here somewhere at 0, 0 basically. And if you see, this is a 400 KSI asphalt, this is 28,000. As you move away, it is about 10,000. So this is the range of change you can see resilient modulus when you are trying to study the variation inside. Okay, so constant value is not necessarily a right thing. Now we are going to look into models. The very first model is sigma 3 versus resilient modulus, kind of K times resilient modulus, and for the tutorial this is a good time for me to start telling you how to do this. Let us say, and again disclaimer, this is not a model that you're going to use all the time. This is very rarely used model, but let's say this is the model we are using. So MR is equal to some kind of a constant K1 sigma 3 raised to the power K2. Okay, people who have done this, please don't answer because you probably know this already. You have done it. I want the others to brainstorm a little, and I want this, folks. I give you a resilient modulus test data, like a test result, and I tell you that I want, for my analytical model, for my finite element model, I want this model form, give me the K1 and K2 values. How will you approach this problem? And people who have done and done this, please don't answer. I want the others to have a discussion here. How do you think we should approach this? Umesh, in your class, did you go over model fitting and stuff in your? No. Okay, good. So people. Okay, but you didn't tell them how to go from the test result to model fitting, or did they do that? Okay. Okay. So we'll okay. So now we're talking about a test data. So does everybody understand the question, what I'm saying? You have a test result, you have a full test result, and now I am asking you, give me K1 and K2. How do you think we should approach the problem? Yes, but how? That's the exactly right answer, but how? How do you develop the correlation? Thus, the first step you said, elaborate that, teach me how to do that. Okay, okay, you're going ahead, but I'll go with you because we are not there yet. But okay, log MR is equal to log K1 K2 log, okay, y equal to mx plus c. This is c, this is x, this. That's what you are also saying, right? And then what do you do? We have the data point. How many data points we have? 15. We have 15 data points, right? So we have 15 data points. So you are taking the MR, then you have sigma 3, fit a linear equation, log blah blah blah, you do that, and then what happens? So K1, so this is basically C, so C is equal to log K1, So K1 is equal to 10 raised to the power C and stuff like that. Easy. Everybody? Viswandita, did you follow it? I want the undergrads. Pushpak, are you okay? Or MTech, just first, did you follow this? Please, let's continue because we are going to do this in tutorial. So let's slow down. What do you have in your MR test results? You have all the stress states that did you apply it or did you get it? Applied. Stress state is something you apply. And what did you get? MR. So you have MR and sigma, all the sigmas in your test result. And how many do you have? 15. Right? So you are going to say, I am going to plot log MR versus log of sigma 3, and I am going to fit a straight line to it, and my model formulation says it should look something like this, and I am going to just decode the parameters, model parameters. Good. Then that is y equal, then we have K1 and K2. So that's basically what is going on here in this case. You find K1 and K2. Now you have a beautiful thing with you. You are like, here is your K1, here is your K2, now go and run wild. Run any layered elastic analysis, determine sigma 1, sigma 2, sigma 3 at any point you want, put K1 and K2, that's the modulus at that point. Right? So now you have a complete distribution. So that's this one. The most common one is called the Hicks and Moniz-Smith model that you will come across all the time. It's called the K theta model. K theta model. Theta, as I have already explained to you, is bulk stress. Sigma 1 plus sigma 2 plus sigma 3. And you are plotting it against theta and MR, exactly the same thing. You fit your model. Instead of this, now this becomes theta, this becomes theta. Right? Question? Please ask. I don't have a problem going over this again. Go ahead. Oh, here you're saying, why is it doing that? That's a good question. I'm glad you caught that. Why is it doing this, folks? This is sigma 3, right? You're talking about one psi of sigma 3. That's the log. It's a log scale, but it's 1 psi, and the minimum theta you are applying is probably about 4, 5 or 6, because theta is sigma d plus 3 sigma 3, right? So you're already on the right hand side. Good catch, but yeah, it's just the nature of the value, nothing special. Are we good on this one? K theta? What do you think is the problem with the K theta model? Again, people who have done this, who have studied this, don't answer. But if you have not, everybody is open. Can you say that again? Yeah. I mean, if the data, I mean, the model is in log, so that's why it's historical. It's in log scale, by the way, right? So it's the same thing, K theta to the power n. Here is my question, folks. Theta is sigma d plus 3 sigma 3. Let us take with a stage sigma 3 is equal to 3 psi, sigma d is equal to 1 psi. So what is theta? 10 psi, right? Second stage, sigma 3 is equal to 1 psi, sigma d is equal to 7 psi. What is theta? the k theta model, the modulus value is same. Is the material going to behave the same? Which one is it going to be stronger? Much more confined, right? So in the k theta model, you are not able to isolate between the effects of confining and deviatoric effects. Do you understand what I am saying? It works. K theta model works all the time. It is the easiest model to use. It is the most common model to use, but there is a limitation. It doesn't isolate the effects, because the effect of confining versus the effect of deviator is different. Like what they just said is, for a cement stabilized thing, I'm quoting them, I did not test it, but the effect of confining is very limited. Deviatoric, you see significant effect. In the theta, you can't distinguish that, right? Because it's merging everything into theta. So how do you address it? Pavitra, right? How do you address it? See, these are open-ended questions, so you just shoot for the sky. You just get anything you want. There's no answer I haven't given you, right? How do you address this question, problem? You can phone a friend if you want. Anybody? 3 parameter? Say again? Maybe confinement as a separate parameter. Let's do that. Let's do that, and then I will ask you a question again. K1 times, they are saying sigma 3 raised to the power K2, then theta raised to the power K3. Is that what you're saying? Ah, now we're talking. Now you're separating them, right? So my answer is yes, exactly. You have to separate somehow. But let's not get there yet. There is actually a model called the Uzan model, which we will take a look in a second. Sigma d raised to the power K2, theta raised to the power K3. Professor Jacob Uzan, the smartest person alive in pavement engineering, by the way. If you ever get a chance to interact with him, you'll see. He's from Israel. He's a walking genius. Developed this. I have a very interesting story about J.K. Bhujan, I'll tell you. So when I was a grad student, there was a conference at TRB. You probably have heard of TRB. So we were sitting, and there is a lady who made a presentation from Texas A&M University, and not a faculty, a postdoc. She made a presentation, and she kept citing some work that Robert Litton or Bob Litton, that's another name if you in pavements you'll read all the time, Bob Litton and Uzan had done. So she kept citing that, Litton and Uzan did this, Litton and Uzan did this and everything. So finished the presentation, and this old man stands up and he says, can you go back to this equation? I don't think the equation is derived this way. And the lady's answer is, no, Dr. Litton and Dr. Uzan did it this way. And he's like, I am Uzan, I did not do it that way. And the funny part is, of that postdoc was sitting right there next to me, actually, and that's it. He was sitting right to me, and he could not say, it's a room full of people, and he's like, that is Uzan, you idiot, that's Uzan, right? So finally Jacob says, I am Jacob Uzan, I did not do it that way. But anyway, so yeah, those kind of things happen. But what Professor Uzan did is he separated this, right? He just made k theta into a 3 parameter model. There is a little challenge with this one. What can you think? Yeah, it's overfitting a little bit, right? Because theta already has sigma d in it, so you're kind of using it twice, right? But there is some reason that I don't know that it was done like that. Oh, by the way, this is just k theta data. We'll take a look at k theta values very soon. Actually, maybe we should cover a little bit here. You can have representative values for k and theta. General trend is that as theta increases, or sorry, as k increases, n decreases, you kind of have a reverse trend, and so you can actually predict kind of. So in my dissertation, I should have had that plot actually. So this was by Professor Matt Witzak and Gonzalo Rada back in 81. They actually had an R square of 6.68, but as I said, my PhD dissertation was all about, you know, aggregate testing and stuff, and it was a limited data set. We used Illinois aggregates, but we had about 270 data points, and we had a R square of about 0.92. So if you have a consistent testing effort, you can actually predict n from k. It's actually a pretty nice reverse correlation. As k increases, n decreases, you can actually predict materials. It becomes very important when in modeling and stuff. So this is Hicks and Monismith, and then Professor Uzan changed it. Theta, oh, I probably wrote it the other way. That's fine. It's just two different parameters. One is theta, one is, yes, right here. Well, there must have been a reason. I don't know the answer to that, so I'm not qualified to answer. I mean, they probably tried to isolate the, or to separate the sigma d effect, because, okay, I kind of know the answer, but I don't want to say it very strongly. So deviatoric is a standalone effect, whereas bulk stress is actually the whole thing that helps with confining. Like what I'm trying to say is sigma 3 is not the only thing that helps the specimen. It's the entire bulk that helps the specimen. So you can think of it as sigma d is the torture component, as the other component is the helping component. That's how he tried to isolate it. But yes, it is a little bit of an overestimation. Then in UT Austin, they separated it into sigma d and sigma 3. But honestly, the Uzan model is actually much more used than anything else because of the bulk effects and stuff. Again, this is just fitting of data. We'll do that this afternoon, so I'm not really spending time on that. This is what I will show you. I'll show you a MATLAB code that I had developed when I was doing my PhD. For all my test results, for everything, I used to like model. I used to fit, like, you know, k theta model, Uzan model, MEPDG model, which we'll get into and stuff, and we used to do some relationship in there. Oh man, this is not looking good. Let me see if I can. Give me a second, folks. If I can boot it on Windows. Otherwise, it's going to look. Okay. So, oh, this is a good point for us to discuss something, because we're going to get into model fitting. So let's do that right now. mr is equal to k theta raised to the power n. What is the unit of mr? Say again? Megapascal. Good job. What is the unit of theta? Megapascals? What is the unit of k? Okay. Is your equation right? Why not? Dimensional inaccuracy, right? I mean, no matter what you do to k, it cannot take a square root like raised to the power 1 over n for this, right? So what the heck is going on? Yeah, but you still, I mean, yes, they are empirical formulas, but they are still, representing stress strain behavior and stuff. So how do you address this? Make theta unitless. How do you do that? Okay, so now he's talking. So either P naught or PA or something. Now you're doing n. So now what is the unit of this ratio? Unitless. So what now happens to the unit of this? Kpa, mpa, or whatever, right? So pay attention to this reporting your test results, right? When you're writing papers, when you're writing tables and stuff, make sure this is consistent. Blindly say k is unitless. If it is k is unitless, your model is wrong, right? So these are little things. This is called nitpicking, but you have to be particular about these kind of things, right? Another thing I think what Akshay said is you can also develop divided by PA. What is PA? What is the value? 14 point? Is it 3 or 7? Is it 3? I don't remember. I think it's like 101.3 kPa, right? Whatever that is. I don't remember exactly. But just remember this, that if you, both are correct approaches. Theta k theta, you always do P0 because you divide by 1. Otherwise, you do realize that your model parameter values are going to change, right? Whether you divide the theta by 1 or whether you divide by 101 or 14.7, your model parameter values are going to change. So just pay attention to what you are trying to do. So for k theta, it's more common to have divide by P0, which is 1 kPa. Just the same. You're just making it unitless. Okay. Then there is something called Leyden-Nelson's model. Again, I1 is the same as the first stress invariant. J2D is basically the octahedral tau shear stress. We'll get into that. Octahedral shear stress is again another mechanics thing. By the way, who can answer me senior PhD students or whatever question? What is a stress invariant? No, that is first stress invariant. I said what is invariant? With no, I mean invariant is an invariant. I mean it can be summation, it can be expression or something, but the question is it does not change with change in the coordinate system or something like that. Whatever you do, it remains the same. The magnitude does not change, right? So that's what first stress invariant is. So tau octahedral is another definition that comes from mechanics, okay, and it is defined as 1 over 3 root of sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Okay, now let's do it for a for a triaxial, typical cylindrical triaxial test. What is sigma 1 minus sigma 2? Sigma d. What is this term? Plus what is this term? So 1 over 3 times 2 times sigma d square root whole thing is square root 2 over 3 times sigma d. That's called octahedral shear stress. Okay, that's also sometimes written to as the J2D. Okay, that's what this is. Oh no, no, J2. I think there is a problem here. It should be Q. It should be J2D is Q square or something. But anyway, it doesn't matter. What matters is some of the models have tau octahedral in there. Okay. Now we are trying to see what is happening. There is this thing called universal model. So now look at this. It has a theta component, which is bulk stress component, which is helping the system. It's a tau octahedral component or a shear component, because remember, tau octahedral in a cylindrical thing is nothing but a sigma d. Is the torture component. It's the deviator stress component, right? And that's the shearing. That's what's hurting the system, right? You're isolating those two. And then this is also P0. Then they changed it a little bit to MEPDG, where they did this, and then they introduced PA in here. Okay. There is a term here, +1, that magically appears. Okay. And I'll give you a hint. The existence of a +1 is a very funny reason. It's not a scientific reason. It's a very funny reason. Tell me what. Yeah? Yes. Whole equation collapses. Your resilient modulus becomes 0. So it's an artificially cooked way to make it non-zero. Right? It's not based on mechanics. It's based on mathematical manipulation. Right? This is called the MEPDG model. Okay? In our tutorial today, we're going to look at all three. We're going to do K theta, we're going to do Uzan, we're going to do MEPDG. Question, Atanu, were you raising your hand? No. We're going to raise all of that. Okay? And in this case, look, pay very close attention to your model formulations. There is a PA here. You are multiplying PA. So what is K2, unit of K2? Sorry, K1. Unitless. If there was no PA, what would it be? Megapascal or something, right? Pay attention to how the model is defined. I see a lot of times in literature, people just coming up their own version of things and stuff. It's not fair. You have to give credit to people how defined it the way it should be defined, and then pay attention. Any questions about this? Straightforward, right? We should be able to fit models. Level 2, design, right? What is level 2? We have something else and we are going to predict, right? So correlate from empirical lab tests, obtain MR from CBR, which is 55 plus 555 R or 2555 CBR raised to power 0.64, obtain MR from PI or gradation properties, convert agency layer coefficient into this and stuff. So now you are trying to relate structural coefficients into resilient modulus, which is a little bit of a far too fetched. But again, if you don't have anything, you have to do something, right? I don't agree this is really level 2, because A is not really that you are determining by testing anyway. A is kind of an iffy parameter. There is DCP and CBRs. There is level 3 where you don't have anything. You have like A7, like AASHTO classification, or just subgrade soil properties like a geological survey or something, like for this I'm going to use this, right? It's basically like, you know, all cars are red, right? So it's basically it's very far-fetched, but you have to use something, right? So that's factors affecting MR, primary factors. It's stress dependency, so applied stress states, sigma 3 and sigma d are very, very important, and then all the other factors like dry density, moisture content, fines content, right? Freeze thaw effects, it collapses and stuff. Again, for different, this is what I tell is extremely carefully developed, you know, empirical correlations. Like, yes, these are absolutely empirical, but they are now, you know, including water content, and they're now including dry unit weight and stuff like that, whatever they have found. It's not really purely mechanistic, but there is also a theta effect and stuff. Okay, so this is actually from one of our studies at Illinois. As water content increases, aggregate base with 12% fines, as the water content increases, it starts collapsing and stuff. So you have to really pay attention to moisture content. Moisture is the biggest enemy for your unbound materials. Okay, angularity, as the percent fracture faces increase, your resilient modulus increases. Its angular interacts much better and stuff like that. Okay, crust and unit weight, this is just errors. Repeated load triaxial testing, this is neural network stuff, let's not worry about it. Crushed gravel versus crushed aggregate versus gravel. Tanmay was asking me yesterday. See, this gravel is basically river gravel, like river pit gravel. It's not crushed. You just go to a river pit, you excavate, you grade it, and that's it. That's how it's sold. It's natural gravel and stuff. So it's very rounded. So as the crushed material increases, your resilient modulus increases significantly. Versus at the blend, you actually have somewhere in the middle. So this is actually one of the studies that was said is, if you really have to use uncrushed material, at least blend it with some crushed material to increase your response. I mean, improve your response. This is my PhD study actually, Mishra and Tutumler. This is actually gravel with 0% non-plastic fines, optimum. Limestone with 0% non-plastic fines at optimum. And as you can see, this gravel is again an uncrushed gravel. So it's actually much flatter at the bottom. The crushed material gains much more stiffness. Stress hardening effects are much bigger and stuff. This is another angularity. This is the dissertation I sent you, Tanmay, the Tongyan Pan's work. And this is basically angularity and surface texture. As the angularity increases, so we haven't talked about this, but you know, aggregates, the angularity, there is a way to quantify it by image processing. It's called angularity index. We'll not go into the details. Higher angularity index means it's a very angular material. Lower means it's uncrushed kind of stuff. So as the angularity index increases, resilient modulus increases significantly. As the surface texture increases, now we are not talking angularity, but I am talking now the roughness of the surface. That also increases your modulus. So you see that significantly here. This is something related to modular ratio. I'm going to skip this for today. We're going to talk about anisotropy later. This I don't want to get it lost into anisotropy. This is another thing. Higher fines. This is again 4% fines, 90% of optimum. 16% fines, 90% of optimum. So the same material. So this is all engineered gradation. So my the year of 2006, the entire Christmas time, like from November mid to mid January, I was in a sieve room sieving like maybe 2 or 3 tons of aggregates. That's all I was doing. So this is all engineered, like every aggregate. So 3 aggregates, limestone, dolomite and uncrushed gravel, they were separated into big drums by size. So I would basically take 2-3 shovels, sieve it, separate into drums, keep doing that, and that is what my entire PhD was on. So this is all engineered gradations. As the amount of fines increases, because fines are fine grained stuff, not coarse grained, so you're not gaining as much stress hardening. So a low percent fines, your material is more stress hardening. As you start inducing more fines, it actually reduces the stress hardening property. So that's what this is. This is aggregate layer stiffness. You know, it's a nonlinear function of applied stress states. And then advanced aggregate testing, we need to determine what is called as directional dependency. Okay, what happened here? Why is it not changing? Okay, so we have about half an hour, right? Yes, exactly. I think this is something we can get into. Okay. Umesh, so this has a continuity. Okay, I mean it's a lot bigger. So what I am thinking is maybe in the next 30 minutes we will start looking at the models and stuff, and then continue that into the tutorial and the back calculation today, so that this we can cover tomorrow. Is it okay? Yeah, I mean everybody is here. I mean, yes, it's being on, because this models and stuff is going to be a lot more hands-on, so it's for the online people it's probably not as beneficial and stuff, but we can do that. I don't want to spend half of it today, or maybe I can just give you the concept. Yeah, let's do the concept. I don't want to change the pattern. Okay, let's revisit this, folks. Who remembers what did I say the concept of sigma 3, sigma x and sigma v? What was the relationship yesterday? We talked about this. No. Inequality in a triaxial, in a typical triaxial testing. This is what? This, right? But we said that's not always the case. There is going to be extension states and stuff like that. So that is where this advanced triaxial testing comes into picture. Okay, and we are going to separate this now. So I'm going to draw the same sample now, but I'm going to separate this quantities. Here is what I'm going to say. I'm going to say this one, I'm going to say sigma h comma static plus sigma h comma deviator. Okay, and this I'm going to call sigma v comma static plus sigma v comma deviator. Do you understand what I'm saying? Right? Until yesterday we were just talking this at sigma h horizontal, and this we still had kind of sigma h or sigma 3 plus sigma d, right? Now I am not worrying about sigma 1, sigma 3 or anything. I am talking horizontal, vertical, pure separation, and I am saying some magical way I am going to say there is a static and there is a deviator component here, and there is a static and there is a deviator component here. Does that make sense what I am saying? Okay, now what I am going to do is, this is probably going to be a good exercise. Let me see, hold on. Instead of washing, it's probably better to drink it. Okay, So now we are talking about a specimen. Okay. I somehow come up with a magical way of having a sleeve like this. Okay. And my specimen is in this sleeve. Do you understand? The triaxial specimen is in the sleeve. And I have a magical way of separately applying vertical stress here, and I have a way of confining it this way, right? Now you see the difference. In the past, what we used to do is we used to keep it in a chamber, so the same air pressure was confining all the way. Now I am separating it, because the way, why, when it was the same air pressure covering, I had no way of making sure that the horizontal is greater than the vertical, because at least the vertical is feeling the same as the horizontal. Now I am separating it. I am now holding it this way. So now if I am holding it, I can squeeze it this way, can't I? And if I have a separate mechanism here, I can pulse it separately, can't I? Now you see that there is independent control over the lateral and the vertical, right? So when I do that, now I am getting one step beyond our conventional triaxial testing, right? So the test method we are going to get introduced to now, it's called the University of Illinois fast cell. That's basically the concept. This cup is this box. It's a cube. The cube is full with oil, hydraulic oil, and inside that there is a membrane, and that membrane is basically creating the effect that my hand is just creating. And there is a actuator which you don't see at the back connected to that oil, where I can pulse it, pressurize the oil so that it squeezes the sample. Do you understand? And the vertical is just a vertical. I mean, any, just whatever you have seen, what you have done, right? Now what can I do? If I want to run a standard triaxial, conventional triaxial test that you have been running, and we are talking resilient modulus, not shear strength, resilient modulus, what should be the relationship between sigma Vs and sigma Hs? S stands for static. They are the same, right? So sigma Vs is equal to sigma Hs, and what is sigma Hd? 0. And what is sigma Vd? That's your conventional triaxial testing, right? But this is just one special case. I do all sorts of fancy things on this, right? This completely opens me up for everything I want to do. I can set sigma Vd is equal to 0, and I can pulse this thing in the horizontal direction, right? Why is this important, folks? What did I say? When the wheel moves, what happens to the principal strain's direction? Moves, what happens? To test it in the lab, you would have to rotate your specimen. How possible is that? It's not, right? It's an unbound specimen. You can't make it horizontal, it's going to collapse. So might as well develop a test system which has independent control in my vertical and horizontal, and now I can do everything and anything I want, right? That is this advanced triaxial testing called University of Illinois fast cell. That is basically what, you know, my advisor and somebody else came up with, and this is what they won their awards on. And essentially he has made like a majority of his career based on work like this. These are some inner views. So this is the actuator in the horizontal at the back. You can just push it. This red thing is the dummy specimen. It's the specimen inside the sleeve, not the sleeve, the specimen inside the sleeve. The chamber is raised. That's in the air right now, and you just get it inside. And that is what I was powdering. Remember, I told you that I had to powder my specimens because there is a membrane on this and my specimen is in there. So the membrane to membrane friction I have to reduce. So I had to powder the specimen all the time. Otherwise, it's going to collapse and stuff. It's going to shear. So you do that, and then that basically gives you complete independent control over. Look here. The sleeve, just like I did, does not extend to the top, because if it extended to the top, it beats your purpose. You need to have independent control over radial and vertical directions. That is the reason this is separately applied, and now you also have radial LVDTs. I can actually apply a radial deviator stress and measure a radial recoverable strain, and I can actually define MR, H, horizontal resilient modulus. Why is that important? Let's think about aggregates. Now let's go back a little bit into mechanics and classic elasticity and stuff like that. There is a thing called isotropy. What does isotropy mean? Same in all directions, same property in all directions, right? That's true for an aggregate layer. No, because when you compact an aggregate, the particles actually arrange something like this. Right? So if you apply this way, they are sitting on each other and they're resisting. If you apply this way, the behavior is different. So it's called anisotropy. But is it 100% anisotropy? It's still a cylindrical specimen, right? So the horizontal, the x and the y directions are probably similar, and they are different from the z direction or the z direction, right? So there is anisotropic this way and anisotropic, like one set of properties this way. So it's called cross anisotropy. It's not truly anisotropic. It's not three-way. It's called cross anisotropy. So the fast cell represents or models cross anisotropic behavior. You are not differentiating between sigma 2, sigma 3. If you did have a true triaxial system, which is a cubical thing, you could do that. I think Professor Buddhima Indraratna in Australia has a true triaxial for railroad ballast, if I remember correctly. I haven't seen it. I haven't been to Australia. This is the science behind it, folks. Epsilon 1 is 1 over mr sigma 1d minus 2 times nu sigma 3d. Do you remember this? What equation, what formula is this called? What law is this? Poisson's effect, but what law is this? Hooke's law. This is Hooke's law, right? This is what you have seen. So when you do vertical, and epsilon 3 is 1 over mr sigma 3d 1 minus mu minus nu times 1 minus sigma 1d. This, now look, there is a d in both directions, right? When vertical pulsing only, sigma 3d is 0. So this term becomes, so sigma 1d over mr is epsilon r. Isn't that what you are working with to start with? Yes? But if you have epsilon, and in that case, sigma epsilon 3 is just the Poisson's effect, right? Just the Poisson's effect. Horizontal pulsing, epsilon 1 is minus 2 nu times this, and epsilon 3 is the 1 minus nu component. It's just Hooke's law interpretation, There is no difference. But what you do see is, look at epsilon 3 in vertical pulsing and look at epsilon 1 in horizontal pulsing. What do you see the difference? Gets doubled. Why? Say again? Yeah, because x and y, there is a 2 as well, which we are not counting here, right? There's a 2. It's a three term equation, right? That's why it's happening this, right? So this is the advanced triaxial testing concept of pulsing it in different directions. Okay? So this is CCP m equal to 3. This is basically the standard testing, and what you can do is you can have sigma. Look here. Now deviator stress is written as sigma nd. It doesn't say V or H, it's N. It can be anything. You can pulse in any direction, right? And then you can actually see things like you can do the testing approach, checking and stuff. And I actually did the exact same thing, and this is on the red specimen. This specimen, it's plastic. It's like not plastic, like synthetic rubber or something. So is it dependent? No, it's constant modulus. So irrespective of which way you pulse, you should have the same, and it's isotropic, right? That's what this data is saying. You're proving it that either way you pulse, you measure the same thing, right? Then the fun starts, right? Now you are talking about MRV is the closed and MRH is the open. Now you're talking vertical modulus and horizontal modulus. Now you're quantifying anisotropy, cross anisotropy. Why is that important? I will tell you when we go into modeling and stuff, right? Now the fun starts. Look at this and look at this. So the horizontal is significantly lower than the vertical, right? What are you doing when you are modeling in layered elastic or traditional FEM and whatever that? You assign the same, right? So you are significantly over predicting, overestimating the horizontal modulus. So you are significantly under predicting the responses. When you consider anisotropy, your response will be lot. So you're like, oh my God, my finite element model, which is really fancy, is giving me 100 microstrain, but in the real world I am seeing 150 microstrain. Why? That's because you are assigning the same modulus in vertical and horizontal directions. It doesn't work that way for an aggregate. It's anisotropic. You have to separate it up, right? Very, very limited implementations, purely research. I mean, it's not been implemented into practice, but this is what that Fred Burgraff Award paper he won back in '99 and stuff for this. This is what you have seen already. Stress path is rotating. Measure principal stress, how it is rotating, what is the degree of alpha is the rotation. You have seen this already, the extensional state and stuff like that. And you can measure and predict all of that or simulate a lot of that using the fast cell. Okay. Now look at this. This is actually from the FAA, Federal Aviation Administration in New Jersey, Atlantic City, New Jersey. They have a huge testing facility. It's called NAS, National Airport Pavement Testing Facility. It is actually one of the major researchers in there is actually an Indian guy, Navneet Garg or Nav Garg. He's a very, very well-known person, another Illinois graduate. But if you see here, these are pressure cells, vertical, horizontal, and these are the states. You can actually see this is real data. This is not theory. This is not schematic. Look here, you actually are seeing extension of these materials. There are stages, time history, where you actually record higher horizontal stress than vertical. So you have to somehow be able to simulate that in testing as well. So that's what the advanced triaxial testing is. This is the QP diagram. We're not going to go into this, how you are going to get into the length of stress path and slope, and what is the slope of the stress path when you are testing. Because you have the independent ability of controlling the two stresses, you can simulate any stress path you want, right, in there. So this is sigma 3, sigma 1, and then it changes as you apply more loads and stuff. So then you can actually test it differently. For top of base, for middle base, you can actually rotate it. Bottom base, you can actually rotate it and stuff, and you'll actually have different stress sequences. So this is variable confining pressures, this is constant confining pressure and stuff like that, which is your Astro T307. Same here, you can do it in vertical. This is the VCP, variable confining pressure. You can actually in a PQ diagram. So by the way, this is the definition, just so that you know. And I think, okay, I think for PQ there are two definitions. I think one is called the MIT definition, one is called the Cambridge definition or something. I don't remember exactly. It's been a while I have gone through this. But this is the definition we are talking about. So Q is nothing but deviator stress essentially, and P is bulk stress divided by 3. So average, mean stress is what they call it. And if you want to run it, you can actually test the materials in horizontal pulsing only. It's actually pointing down at a slope of 3:2. If you do a vertical pulsing only, it's pointing up at a slope of 3:1. So now you are really playing with the stress path of the material, what it is subjected, what it is and stuff like that. This is stress path dependency. I think we can skip these. Let's see what else. That's okay, that's actually good. So 1254. So this is pretty much what I wanted to touch on, this concept. And tomorrow, like today we'll do the modeling on the vertical and the back calculation and everything. Tomorrow I will show you some data for horizontal pulsing, and we'll try to take a look at how that works and stuff like that. So we have 6 minutes. So any questions or any discussions before we break for lunch? How did we evolve into that point? And so the point is the background or the entire derivation of this is from a theory of elasticity and classical mechanics point of view. And in classical mechanics, deviator stress does not really exist, right? So it's the octahedral shear that is actually affecting the shear. It just resolves down to sigma d in traditional triaxial testing. You can't derive a theory for that because it's a very simplified case. So they derive the theory for the full case, which is classical mechanics or theory of elasticity is octahedral shear stress, and then it just resolves down to deviator in triaxial testing. Anything else? Does everybody? We still have 4 minutes, 5 minutes. Everybody has their computers available, right? So let's do quickly. I'm going to show you a link. I'm going to send you a link right now. Let's download or go to, let's visit that link. So go set up your laptops so that we can be productive in the tutorial. Okay, we have a couple of important things to cover in the tutorial today. આપણે બંધ કરી દઈ પાડ્યો સેટા લાઈવ સોરી બંધ. What is anywhere, right? So think about it this way: if the horizontal modulus underestimated or overestimated? Overestimated. So if you assume it is isotropic, so the material is equally strong this way and that way, right? So now if I have a component of stress acting this way, my strain, like you can do a cosine theta and a sine theta. So this component, the strain is in a very simplified way stress divided by modulus. and now you are dividing by a very high modulus. So you are under predicting the strain. Are you following? But if you actually do the real estimation, the strain will actually be higher. So, and what governs, what does strain govern? Your actual performance, like cracking and everything is coming from strain. So what I am saying is, by under predict or overestimating the modulus, your estimated performance will actually be better than what you will see in the real world. That answer your question? No, okay. No, well, no. There is a difference. You are not considering tension, right? Horizontal strain, I mean, the way you define it, horizontal strain does exist because the material does deform, does get displaced and stuff. What we are saying is that it does not resist deformation in this thing, which is called tensile stresses, right? So, but the point is, the entire system evolves or behaves based on components, right? It's acting at angles, and when you are resolving it, this does not only affect this also affects this, right? Because that's the Poisson's effect. When you are applying something here, it's going to go here as well. So what I'm saying is, the composite wise, it's not going to be correct. Okay, folks, what I want you to do is day 3 tutorial RTF, command C, strange, taking a lot of time. Oh, are they ସେମାନେ କ'ଣ କନେକ୍ଟ କରିଛନ୍ତି କି ପୁରା ୱାଇଫାଇ କୁ ଏ ଯୋଉ ହ୍ୟାକାଥନ୍ वाला ୱାଇଫାଇ ଏତେ ସ୍ଲୋ କାହିଁ ଚାଲୁଛି? Okay, it's working now. Okay, look at your WhatsApps and launch that website on your computer that I just sent. Live of karwa.